So this, I'm going to start today off with this sort of table that summarizes what we did last time. Yeah, we were thinking about these problems, these decision problems that involve, all of them sort of have this common property that you give them inputs, as inputs, descriptions of Turing machines, and you want to evaluate certain things about the property, right? Some property in each case of the Turing machine that you give it, right? Like the way we defined A, for instance, PDA was, it's a description of a PDA and a string, and you want to know, does the PDA accept the string? And a DFA and ATM are defined analogously, just with DFAs and TMs respectively. And then this E over here was the emptiness testing problem. You just wanted to test if the language recognized by whatever machine you gave it was empty. And then this EQ over here, the equivalence testing problem, was you give it two descriptions. So descriptions of two computational models, you know, DFAs, PDAs, TMs, or whatever. And you want to know if they recognize the same language, right? And we started looking at, we wanted to determine the decidability of these languages using this tool. And what we were doing to accomplish this was reductions, right? This way of extending sort of the decidability and undecidability results that we already have. And the hope was that, like, as we get a better understanding of kind of what we can and can't do with reductions, we could hopefully develop a technique powerful, you know, like reductions sort of powerful enough that we can leave this abstract land of decision problems about models of computation and automata and languages, and actually start talking about the decidability of the more concrete types of problems you might see in the real world, like the post-correspondence problem, which I introduced last time. Yeah. And today, what we're going to look at is, yeah, maybe it's a bit obvious here, but there's this kind of conspicuous hole in our chart so far. And we're going to try and fill out the rest of this table. And in doing so, we'll develop a reduction technique that we will be able to apply to proving the undecidability of PCP. Yeah. And it's kind of interesting to think about this, because I mean, the trend with Turing machines seems to be pretty clear, right? They're so powerful in some sense that reasoning about them is undecidable. Yeah. And DFAs are so simple that it seems like, well, I mean, reasoning, you can always, like, any question that you ask about the property of a DFA, it seems to be decidable, right? So PDAs are this very interesting playground, sort of, because they kind of straddle the complexity of DFAs and Turing machines. And while we were able to show that the acceptance problem for PDAs is decidable, it's not super clear if that, you know, if that trend is going to continue for the emptiness and equivalence problems the way it did for DFAs, or if maybe we'll find an undecidable problem somewhere around here. Okay. So any questions about what we're going to do today, or what we saw last time that I can clear up before we move on? No? Okay, cool. So we're going to start with the emptiness testing problem for PDAs. Oh, yeah, question. No, you could just say that, like, we know that NFAs and DFAs are equivalent, right? And their recognizability. So the acceptance problem for DFAs is in some sense exactly it's equivalent to the acceptance problem for NFAs, right? Yeah, and that same thing kind of happens with Turing machines even, right? Because we've been, like, all of these problems have been looking at encodings of deterministic Turing machines, but you could very well ask the same question about non-deterministic Turing machines. And because you can always convert between the two, right, in this way that we talked about, though I don't know that we gave like a yeah, because they recognize in some sense the exact same class of languages. And you can kind of construct this deterministic Turing machine that simulates any non-deterministic Turing machine you give me. The results are kind of the same here. But it's interesting that you mentioned that, because with PDAs, the story was kind of different, right? Non-deterministic PDAs, which were kind of the PDAs that we defined by default, and deterministic PDAs weren't equivalent, unlike it was the case with this model and this model, right? It turned out non-deterministic PDAs were actually stronger, strictly stronger than deterministic PDAs. So we'll see if that, like, this is perhaps one reason to suspect that the story might play out a little differently here than it did for DFAs and Turing machines. Good question. Any other questions about what we're going to look at today? Cool. All right. So what we're going to start with is this emptiness testing problem for PDAs. I don't know. Does anyone? So I'm just going to like remind you here how we define this problem. ePDA. It's you give me a description of a PDA, and I want to copy paste error. PDAP, and then the I don't know if my pen will work with me here. There we go. And then the language of P is empty. Yeah? All right. So you give me a description of a pushdown automata, and I want to know if it never accepts any string. If its language is the language that it recognizes is empty. Okay. So I don't know. Does anyone have any like guesses as to whether this is going to be decidable or undecidable? I don't know, just like throw them out there. I'm kind of curious as to what the intuition is here. How many, by show of hands, how many people think it's going to be decidable? Okay. How many people think it's going to be undecidable? All right. Okay. And the rest of you believe in some third option outside of the binary of logic. I'm curious to know about. But okay, yeah, it turns out that if you raised your hand, if you non-deterministically chose that it was decidable, you are correct. So congratulations to you. I don't know, maybe you had some like mystical insight that actually did. Maybe you saw in your mind in the flash of a second after I asked this question the entirety of the proof that I'm about to show you. I don't want to. I'm going to give you guys the benefit of the doubt there. So yeah, it turns out that the emptiness testing problem for PDAs is in fact decidable. And this is one of those things where the proof is sort of simple enough that we don't really need to rely on a reduction to a decidable problem that we already know. It was sort of the case, and that was like, we also saw that with the emptiness problem for DFAs, right? We just kind of searched for anything that could possibly accept in the representation of the DFA. And you can kind of do something similar in the emptiness testing, like for to construct a decider that decides ePDA. And that just kind of works like this. So let me describe at a high level how this is going to work, because it is really simple. We're just going to convert our PDA to a CFG, right? Which we know we can do because when we saw the equivalence of CFGs and PDAs, we did a little more than prove their equivalence. We proved the equivalence by giving an algorithm that converts one to the other. Yeah. And that was kind of like, we relied on that algorithm to prove that this was decidable as well. Yeah. So we're just going to convert to a CFG that is equivalent to my PDA. And all a CFG really is it's a list of rules, right? So if I want to test whether or not my CFG generates the empty language, I just need to ask myself, does it generate any string? Does it generate any terminal symbol? Like, is there some way of getting from the start variable by following my rules one at a time to literally any terminal symbol, right? And so you can kind of do that by just this sort of backtracking procedure where you start by marking all your terminal symbols. of your CFG. And then while there remains a rule of the form some non-terminal symbol A followed by a string W of terminal and non-terminal symbols, where W contains a marked symbol and A is unmarked, you just mark A. So you're just like backtracking kind of up, like you have, okay, these are all of my, you kind of start on step 2 by saying, these are all of my terminal variables. And then on the first iteration of the loop on step 3, you say, these are all my rules that lead to a non-terminal, that lead to a terminal variable. And then on the third iteration of the loop, you say, okay, these are all of my rules that lead to rules that lead to terminal symbols. And you keep doing this until you can't mark anything new anymore. And then you just check. If you marked the start symbol, then you should accept. Or sorry, reject. I mixed this up. Because then there is like a sequence of rules, a derivation, right, that starts with the start variable, goes to a terminal symbol that just generates some string. So the language can't be empty. Yeah? So this should say reject. And this should say accept. All right, nice. That was an easy little warm up. So we're already like halfway there, it seems. Yeah, we answered that this is decidable. Okay, nice. So that leaves us with one final unsolved question about the decidability of these automata languages, which is the equivalence testing problem for PDAs. Yeah, and just to kind of remind you guys how that language was defined, it was, so you give me a description of one PDA, P1, and another description of a PDA, P2, and I want to know, do they recognize the same language? Now, okay, I'm kind of curious. How do we feel about the decidability of EQPDA? Raise your hand if you think it's decidable. Okay, raise your hand if you think it's undecidable. Okay, I feel like surely it can't be that boring, right? Is the thought process here. There has to be some kind of twist at the last moment. And that's good intuition because, well, we'll see why in a moment. But before we actually give an answer to this question and proof, I just want to ask you guys something. So do any of you remember how we showed that EQ-DFA was decidable? How do we do that? Yeah. What do these arrows mean in the table? Right, you are right. Like we did do something like that for the emptiness testing problem for DFAs. Yeah. But then the way that we showed that the equivalence testing problem for DFAs was decidable was we gave a reduction to the emptiness testing problem, right? We showed if you can decide this, then you can decide this, right? So let me ask you something. We showed that the answer to this question was yes, right? There is a decider for EPDA. So can we just do the same thing that we did for DFAs? Can we just give a reduction, like the exact same type of reduction we gave from the equivalence testing problem for PDAs to the emptiness testing problem for PDAs? I'm going to remind you of what this reduction looked like, okay? So the question is, we know EPDA is decidable. Can we just argue that EQ-PDA is decidable the same way we argued EQ-DFA is decidable? Where we gave this sort of, okay, my screen froze. Just scroll down, please. Technology has failed me. Oh, hey, there we go. So this is what we did. This is kind of what we did. So I've just like copied and pasted the reduction that we did for DFAs, right? To show that EQ-DFA was decidable, but I've replaced the Ds with Ps. Like we're just trying naively to do the exact same thing with pushdown automata. So let's recap, forgetting that these were PDAs for a second, let's recap how the reduction from EQDFA to EPDA or EDFA worked. So we constructed, you gave me two machines, right? And we constructed a machine that did what? It recognized the symmetric difference, right, of the languages recognized by the two machines that you gave me. And the way we defined the symmetric difference was it's all the things that are exactly in one of the sets, right? So it's the union of the things without the things that are in both things, or both sets, yeah? And then we say, okay, well, we know that this language, right, this set, the symmetric difference, is empty if and only if what? What has to be true about this set and this set for their symmetric difference to be empty? Yeah, they have to be equal, right? So this is how, now I can leverage my decider that tests the emptiness of a description of a machine that you give me, right? So we can just simulate that decider on this machine that recognizes the symmetric difference, right? And if it accepts, meaning that this thing is empty, right? Then I know that these two sets have to be equal, and I, the decider for the equivalence testing problem, can accept. Otherwise, I reject, right? So does this work for PDAs? Yes. Well, yes. Yeah. We relied crucially on the properties of regular languages, that they were closed under union and intersection, right? So it's not clear that there is a PDA that could recognize this symmetric difference language, right? Okay, so, all right. So we can't do the same trick to show that the equivalence testing problem for PDAs is decidable. Maybe this business about not being closed, about, under unions and intersections, should lead us to begin to suspect that there is a plot twist afoot in the story here, right? So, okay. Now, I mentioned at the beginning of lecture, okay, before I continue, let me pause and ask, are there any questions about what we just discussed? Yes. Oh, we haven't seen it yet. I'm saying that this is foreshadowing. This is all foreshadowing so far. Because what we've established is that because like what we showed is that this is yes, right? And the question we just asked is, last time we showed this, can we do the same thing here to show that this is yes as well? And the answer was no, for the reason that, sorry, what was your name? Ayum pointed out that unlike regular languages, context-free languages aren't closed under union and intersection. Yeah? So this is foreshadowing of the plot twist, okay? Now in the beginning, any other questions before we go on about what we just discussed? Yes. Oh yeah, of course. Mm-hmm. So yeah. So we wanted to know, does my CFG generate some string? And if that happens, it means there's some way of reaching a terminal symbol from the starting variable. Yeah. So what this algorithm does is it starts at the terminal symbols and it kind of walks through the rules of my CFG looking for the start variable. And I mark them. That's how I know that I've already visited one, so to speak, right? So if at the end of this process, I've marked the starting variable, it means I was able to start at a terminal symbol and get all the way through my rules to the start variable. So if I just reverse that walk I took, I have a derivation of a string that means the language generated by the CFG is non-empty. Okay, does that make sense? Perfect. Okay, any other questions about what we looked at so far? Okay. Now, I did mention at the beginning of lecture that the technique that we're going to use to prove this is sort of the same technique that we're going to use to prove the undecidability of PCP. And that's like, so there's a bit of a skill spike here in proving this. And so to kind of work our way up to proving this, we're going to start with a different problem, okay? So I'm going to define a language, all PDA, as it's a description. You give me a description of a PDA, and I want to accept this description if my PDA generates every string. So the language is everything now. So it's somehow, in some sense, like a moral opposite to the emptiness testing problem. I want to know if everything is in that language, okay? Now we really see the sort of a concrete illustration of where the difference, sort of how crucial it is that PDAs aren't closed under complementation, right? The way our DFAs and TMs were. So it turns out that even though we showed the emptiness problem test, like the emptiness testing problem for PDAs, which doesn't seem super different to this, right? It's just kind of the opposite, or I guess it's as different as possible. What I'm saying is the description doesn't seem super different. So in spite of the fact that we showed this to be decidable, right? The emptiness testing problem for PDAs, it turns out that all PDA is going to be undecidable. And that's important because, here we go, we can give a reduction from all PDA to EQ PDA. So if this is undecidable, if we can show this is undecidable, and we can show this reduces to this, then I have proved that EQ PDA must be undecidable, right? And that's going to be our kind of a high level of our plan of attack here. Now, I want to make a note that when I introduced this theorem, when I wrote it down here, I didn't tell you anything at all. Well, okay, I did in the lecture now. I told you guys that this problem was going to be undecidable. But just as it's written here, right, like I just defined the problem. I didn't mention anything at all about its decidability or undecidability, right? But I can still give a reduction for that problem. So reductions, and I want to use this to illustrate that reductions are just relationships between the decidability of problems. Yeah. And when we know things about the decidability or undecidability of the problems that we're either reducing from or to, we can then make a statement about extending that decidability result using our reduction. But a reduction can exist without you knowing beforehand necessarily what the decidability of this problem is or the decidability of this problem is. Okay? And we're going to use a reduction to kind of like take a step in the right direction, work our way towards a problem that seems a little more approachable. So does anyone have any suggestions on how we're going to prove, on just like forget the proof, what would a reduction from all PDA to EQ PDA look like? Like if I give you a Turing machine that can decide whether two PDAs recognize the same language, can you give me a Turing machine that decides whether or not a PDA that you give me recognizes all strings? Does anyone have any ideas on how we could do that? Yeah. Yes, exactly. That's exactly what we're going to do. It's, in some sense, this is the same reduction that we gave from ETM to EQTM, right? Because there we just gave a Turing machine that accepts nothing. Here we're going to give a PDA that accepts everything. Yeah. And so in some sense, all PDA is like kind of a special case of EQ PDA, right? Where you're just testing against this one type of CFG or PDA that just accepts everything. Yeah. And that's exactly what we're going to do. Very simple reduction from all PDA to EQ PDA. You give me in my reduction, so I suppose D is a decider for EQ PDA. You give me some description of a PDA. I simulate this decider on P and P sub 1 here, where P1 is just a PDA that always accepts. Like you can, if you want to visualize what this looks at, like just think of like the transition diagram as being one state. Every character leads to that state, and that state is the accept state. Okay, it's very simple. Always accepts. And then if D accepts, right? So this Turing machine also, or this PDA also generates or recognizes all strings, then I can accept, right? Otherwise, I reject. Yeah, very simple reduction. We've somehow, and in some sense, like all PDA seems a little more tractable to work with because we're only dealing with one PDA now instead of two, right? So, all right. Any questions about this? Yeah, so now we've reduced the problem of showing that EQ PDA is undecidable to just showing that this guy, all PDA is undecidable. Let's see how we're going to do that. Okay, so if you can think back eons ago to Monday, when we showed that ETM, oh, same copy paste there. Well, you guys know what this should say, right? Language of M is empty. But yes, if you can think all the way back to Monday, when we showed that this problem ETM was undecidable, how did we do that? We did this thing where we were like, okay, first of all, we gave a reduction from ATM to ETM, right? And ATM we knew was undecidable, okay? And the way that we did this was, all right, here's a decider for ATM, given a decider for ETM. I construct this like slightly modified Turing machine, M to the W, right? That transforms an instance of ATM into an instance, or rather a non-instance of ETM. Like you give me, I construct a Turing machine where that Turing machine's language is empty, if and only if, or I believe it was non-empty, same thing, if and only if ATM accepts, or the description of a Turing machine M you give me in my ATM instance accepts W, right? So that was how we proved this. Now, I'm going to show a different proof of this today. And the reason why is we're going to be able to really simply, like trivially tweak that proof to get an answer to this question. So we've already shown, right? We've already seen this, that ETM is undecidable. But I want to give a different proof of this theorem, and that'll be informative for what we're going to do with all PDA. So we're still giving a reduction in this alternate proof from ATM to ETM. And that's how we're going to get the undecidability of ETM here. But even though it's the reduction from the same problem to the same problem, the actual reduction itself is going to be very different. Okay? So let's talk at a high level about what the proof idea for this reduction is going to be. Okay? My screen would collaborate with me, please. Okay. Okay. So proof sketch. So I want to make a reduction from ATM to ETM. This means, given a decider D for ETM, we want to design a decider for ATM. Okay? In other words, just kind of breaking down things even further, another way of saying this is, given MW, some instance of ATM, so far it looks pretty similar. We're going to construct a description of a Turing machine, M to the W, that accepts some string, so its language will be non-empty, if and only if M accepts W. Then we can just see if M accepts W by simulating my decider tester for emptiness on that Turing machine that I construct. In other words, we want to design a Turing machine MW such that something exists in the language of MW if and only if M accepts W. All right. So what thing, forget everything else. All I give you is a Turing machine and a string to run it on now. What thing exists if and only if M accepts W? Think back definitions. All I'm giving you is a Turing machine and a string here. What did it mean for a Turing machine to accept a string W? What was the definition? Yeah. Yeah. At the end of what was halting? Yeah, but like there was like kind of, because we want to think of a Turing machine. Yeah. Yes. A Turing machine M accepts W if and only if there exists some sequence of configurations of M on W which halts and accepts. Was that a question in the back? No. Okay, cool. So just to refresh your guys' memories, we say M accepts X if and only if there exists a sequence of configurations that satisfy three properties, right? The first configuration is the start configuration. And do we all remember what this notation here meant? This like state followed by string. This was just a shorthand to tell me what the configuration looks like. The string here is the contents of the tape, and the position of the state in the string tells me where my tape head is in the tape, right? That was just kind of a little notational shorthand we did for configurations. So this is what my start configuration looks like. This is what C0 has to look like. And then for all I up to L, if the configuration CI minus 1 looks like this, then CI better follow in accordance to my transition function, right? This is just the formal definition that we gave. And then for it to be an accepting computation, I need the state of my last configuration to be Q accept, right? So an accepting computation of M on X is a thing that exists if and only if M accepts X, right? Why do I keep talking about this? Well, what decider do we have in a reduction from ATM to ETM? It's a decider that does what? You give it a description of a Turing machine, and what does it test? What was that? Yeah. In other words, if no thing exists. You see where I'm going with this? So our language of this Turing machine MW that we're going to construct is exactly the set of accepting computations of M on W. Because that language is going to be empty if and only if M rejects W, right? So this is one way, like looking at the computation histories of my Turing machine, that I can construct a decider, a reduction R. And that's exactly what we're going to do, okay? So before we look at the fine print of the proof, are there any questions about the high level, the idea, the intuition? Honestly, if it seems a little unclear, that's fine. I'm sure it'll all make sense when we look at the proof in a sec, but yeah. So, okay, how are we going to do this? So let's forget, I'm not going to give the reduction yet, okay? Because remember, in our proof idea, we wanted to construct this Turing machine MW, like what would a Turing machine whose language is the set of accepting computations of M on X look like, right? That's what we want to talk about first. So, okay. here's how that Turing machine is going to look. So if you give me some Turing machine M and some string W, like this is an ATM instance, right? I'll define a Turing machine M to the W as follows. So on input, now my input is going to be a possible sequence of computations, okay? I am going to, the way that this Turing machine can check if this is an accepting computation is by checking exactly the 3 conditions here that we gave in the definition, right? So the first thing that it's going to do is check that C0 is the starting configuration on input W, okay? If it's not, so we're going to design, the way we're going to design this Turing machine MW is that its language will be exactly the set of accepting computations if they exist. So we want, if the language is empty, that means there is no accepting computation and M rejects on W. And to reflect that, if we fail to be an accepting computation after this first check, whether C0 is the starting configuration, then we immediately reject. Okay? Can't be an accepting computation. Now we're going to check the second condition. So for all my other configurations, I check that Ci follows from Ci minus 1 in accordance with the transition function of M. Okay? And if I fail this condition on any of these guys, then I reject. If I ever find a configuration that doesn't follow from the last thing, I'm done. I reject. Okay? So, and you may be wondering, well, it's all fine and well to talk about this at a high level, but like, actually, how do we do this? How do we implement this? Yeah? If we were thinking, if God forbid someone asks you to design a formal definition of a Turing machine that did this mess. I mean, the way you would do this is you could think of this input as being encoded as like the contents, like C0, right? This notational representation that we had. Maybe like some delimiter symbol, a pound sign, followed by C1, a pound sign, C2, right? And so you can give it this string that represents the computation history. And really, each configuration kind of changes very locally, right? Like the change is only going to happen around where the tape head is. Yeah? So it's really not hard for a Turing machine on seeing this to check if this is of one of, like Ci is of one of these forms, right? In essence, what it's going to do is it just wants to make sure that everything to the left of where the tape, like the next modification can be, is the same, and everything to the right is the same. And we saw how to check that 2 strings were the same. It was like one of the first things we did with Turing machines in the course, right? You could just sort of zigzag back and forth, right? Except the one difference here is that when you get around this middle portion, you just want to make sure, like your Turing machine is going to look at, because it has access to this description of this transition function, right? So it's just going to look at it and make sure that it follows, or it's going to look at this, sorry, or this rather, and make sure that it follows from the previous configuration. It can go back here, make sure that like, yes, everything's kosher here, move back, check the rest of the string, and repeat that for all my other like encoded configurations. Okay, yeah, question? One tape actually runs M on W. Oh yeah, I suppose that's like, you're saying just, I see, like simulate it on one tape and make sure that each configuration. Yeah, I suppose that's another way you could do this. Yeah, it's just like, it's kind of in some sense, a bit more work than you need to do because of how local the changes that a Turing machine makes at each step are, right? And this locality of Turing machine computation is important for a lot of things that, and we'll see some of those things hopefully a little later on in the course. But like, in fact, we'll see one reason why today. when we actually start considering all PDA instead of all TM. But okay, this froze again, maybe, possibly. Can I move? Okay, yes, I can move. So we can check in step 2 to make sure all of our configurations follow one after the other. And that just leaves checking the final condition in step 3, which is that the state of CL is Q accept. And if it isn't, then we reject. So do we all agree that this Turing machine has a non-empty language if and only if M accept W? Or are there any questions about that based on what we just did? Okay, cool. So, all right, now that we've defined the encoding of the Turing machine that will feed into our decider, right, for the reduction, let's take a look at the actual reduction itself. Fortunately, the reduction is really simple because we kind of did all the work in this first step. So remember, we're giving a reduction from ATM to ETM. So I'm going to suppose, towards a contradiction ultimately, that ETM has a decider D, okay? And I'll use that to construct a reduction R that'll allow me to decide ATM. So on input, some instance of ATM, I construct this Turing machine MW, the description specifically, from the description of the Turing machine that I've been given, NW, right? Note, we're not simulating this Turing machine. We're only constructing it. We're only writing its encoding so that we can feed it into D. Because this Turing machine that we've encoded here, right? Yeah, we're not, our job isn't to run it. All we care about is feeding it into our decider, okay? And then we simulate D, our decider for ETM, on this encoding of the Turing machine that we just constructed, right? And if D accepts now, what does that mean? It means that the language of this Turing machine was empty. But the language of this Turing machine was exactly the accepting computations of M on W, which means that there is no accepting computation of M on W, and therefore, we, as the decider for ATM, should reject. Okay? And otherwise, there is some accepting computation. The language is not empty, and we should accept. Yeah? We all understand how this sort of worked. Yeah, question. On the encoding of the Turing machine that we just described. Yeah, the description. Yeah. Oh, we're not looking at equivalence testing, the equivalence problem. Remember, all we're doing so far, we said, yeah, sure, we can think about the equivalence testing problem, but thanks to this reduction that we gave, right? All I need to do is prove that this is undecidable, to show that this is undecidable. So all we're thinking about now is this like all PDA problem, right? Or that's where we're going, kind of. Right now, all I did was I gave an alternative proof of, where is it? That ETM is undecidable. And what we're going to see next is how we can very simply modify this proof to get a proof that all TM is undecidable. And then from there, we'll see how to simply modify that proof to get a proof that all PDA is undecidable, and then we'll be done. Okay? Yeah, question. So we get a configuration and accept. But if M doesn't accept W, how can we get that? Oh, I see what you mean. So these inputs here, right? Sort of the language of MW, like the strings, if it accepts a string, it means that that string has to be an accepting computation, right? But we can feed as input to MW non-accepting computations of M on W, right? That's the thing. We, as the simulator R, we are never going to construct any of those configurations or any of those computations because there could be many of them, right? Infinitely many of them, in fact, right? And so we're letting our decider for D or our decider for ETM kind of handle those infinite possibilities for us. Does that make sense? Because we never explicitly construct an accepting computation of M on W. We've just constructed a Turing machine where if you give it a sequence of configurations, it will accept on that sequence of configurations if and only if it is an accepting computation of M on W. Yeah. That's really, and of, yeah, exactly. And of course, I guess there is one final, yeah, no, that's correct. Yeah. It's really only to check that kind of starting configuration there. Okay, any other questions about this, what we've done so far? This idea of turning computations into a language of some Turing machine that we can feed into a decider. This is, some people call this reduction method, they call it a reduction via computation histories, because we sort of converted computation histories of the Turing machine we want to know something about into inputs of some language, right? Or instances of some language. Yeah? Okay, well, if there are no other questions, I'll pause here for a sec. Okay, let's see how we can switch this up a little bit to get a decider. So this was what did we prove here? We gave an alternative proof that ETM is undecidable, right? Let's see how to change this or tweak this proof slightly to get a proof that all TM is decidable. So we're not quite where we want to be yet, because what we want to show is that all PDA is undecidable. But what we're going to do first is we're going to show that this other problem that seems even closer to the thing we want now is in fact undecidable by modifying the proof we just gave. Okay? So this proof looks really similar to the thing we just did. We're kind of just flipping some accepts to rejects and vice versa here and there. And so what I did to contain all, like to actually have something written down here, is I just copied and pasted the thing that I just gave, and everywhere where something changed, I wrote it in red. Okay? So here the proof idea now is going to be given, so we're doing same thing, a reduction from ATM to all TM, which means given a decider D for all TM now, we want to design a decider for ATM. In other words, given some instance of ATM, now we're going to construct a description of a Turing machine that rejects some string if and only if M accepts W, right? Whereas before it accepted some string if and only if M accepted W. Now it's going to reject some string. Why? Because if it doesn't reject some string, then its language is everything. Yeah? Then, sort of same idea, we can see if M accepts W by simulating D on this thing MW that we're going to construct. And so now it suffices to design this Turing machine MW such that something doesn't exist in the language if and only if M accepts W. We're just sort of flipping the logic that we just gave. And let's see how we can modify the proof to do that. So the description of our Turing machine MW that does this looks very similar to what we did before, except now I'm still checking these three conditions to see if this is an accepting computation, except whenever I violate one of these conditions, instead of rejecting, what I'm going to do is I'm going to accept. So every either incorrect encoding of a configuration or of a computation, or every rejecting computation means that MW here is going to accept on that guy. So it'll only ever reject if this is a computation of M that accepts W. Now, right? And so, okay, same thing as before. Now we suppose all TM had a decider D, and we're going to define this reduction R from ATM to all TM as follows. So we construct this description, same as before, from the ATM instance that you give me, and I simulate my decider D on input MW. And now what this guy does is it tests if MW accepts every string. But if D accepts some string, it means that what? It is not an accepting computation of M on W. And so if it rejects some string in particular, the only way it could possibly reject some string, or that something could not be in its language, that its language could not cover everything, is if there is in fact some accepting computation of M on W, and so we should reject, right? Otherwise we accept, same as before. So this is a proof that shows that this language, all TM, right, is the language recognized here, everything, undecidable. And now we're really close to what we want, right? Because what we wanted to show was that all PDA was undecidable. Yeah? And, oh, just kind of as a quick note before I pause and ask for questions. So we gave this kind of alternative proof here. We gave that alternative proof of ETM before, right? But the original proof of ETM we did something different. It was a little simpler, right? It turns out that you can prove that ATM is undecidable with a simple variant of that original proof that we saw to show the undecidability of ETM last time. But again, I'm illustrating this because of where we're headed, kind of, where we want to go with this undecidability of all PDA. So now the central question is, all right, how can we take this proof that ATM is undecidable, or that all TM is undecidable, and instead change it so that we get that all PDA is undecidable? So now we want a reduction from ATM to all PDA. And we're doing something that we've never done before. We're kind of straddling the rows of that table we saw earlier, right? We're giving a reduction from a property testing problem about one model of computation. Yeah, and we're saying if you give me an algorithm for that, I can actually construct an algorithm for testing a property of some stronger model of computation. Because all the reductions that we've given so far were from problems about Turing machines to problems about Turing machines, problems about DFAs to problems about DFAs, right? And now what we want to know is, can we do something different? Is there a way we can take this proof and change it to show that all TM or all PDA is undecidable? So what would need to change for that to happen? Well, let me pause for a sec, because if any of you have any questions about what we're going to do or about the proof that we just saw so far, please feel free to ask now. I need to hydrate, so. And in the meantime, you can sort of think about that question of like, what would need to change? Can everyone sort of see, okay, it's a little small because I want to show the entire proof. Any ideas about what should change to get a reduction to all PDA? So, well, let's start by looking at this part of the proof, this reduction that we give, right? So now I'm still designing a decider for ATM, right? Which means that my input instances aren't going to change. I'm still going to give you some description of a Turing machine, and I'm still going to give you some string W. Yeah, and I want to know if that Turing machine accepts that string. But what do I have now? I don't have a decider D for all TM anymore. I have a decider D for all PDA, right? Which means that this thing that we construct here that satisfies this property of it accepts everything if and only if M rejects W, we don't want this to be a Turing machine anymore. Yeah, we want it to be a PDA now. So is there some way that, like, did we really need a Turing machine to recognize this language that has this property that we want? Could we have done it? Could we have designed this M to the W thing here using a simpler model of computation, say a PDA, P to the W instead, that had the property that, well, the language accepted by P to the W is going to be all strings if and only if my Turing machine M rejects W. So let's take a look at this guy, right? Because now that essentially the question we want to answer is, can we turn this Turing machine into a PDA that recognizes the same language? That's what we want to do, right? Okay, let's see. So as I mentioned earlier, here is some possible encoding, right, of a computation of M on W. In other words, maybe this is some input that my Turing machine M to the W from the proof that we just saw might receive, right? So it has like some characters here that are the notational, that represent the starting configuration, C1, C2, same for all these guys, all the way up to my last guy, and they're delimited by these pound signs, right? Or any symbol that isn't in my input alphabet or tape alphabet. So, okay, I want you to imagine that you, yes, you are a Turing machine. How are you going to check that each of the conditions 1 through 3 are met as you go through this input? How would you do that? Well, okay, the first thing we have to check, right, is this the starting configuration? And I can like hard code into, like I know what the input W is, so I can just manually check, oh, yep, that's the starting configuration, and then make sure that the rest of this tape is the input W, right? Like I can check that as a Turing machine in a forward pass, okay? Now I need to check that each of these CIs follows from CI -1. And I can do that by just like zigzagging back and forth, yeah? And checking that the strings are the same, except around where the tape head is, because that's where my change indicated by my transition function is going to happen, right? And then at the very end over here, I've checked that CL follows from CL -1, and I just want to go back and say, oh yeah, by the way, that's the accept state, right? This final configuration contains the accept state. So, okay, you've imagined yourself doing this as a Turing machine. Now, one of the big advantages that we saw Turing machines had over PDAs was that it could like modify and overwrite its input. But we didn't really rely on that when we were checking this, right? We never really left, in fact, the chunk of tape that the input was encoded on. And we did it kind of more or less with just this forward sweep through the input. Because remember, PDAs can't backtrack. It reads an input character and it can never access it again unless it puts it on its stack, right? So, okay, this is starting to look like maybe we don't need a Turing machine to do all of this, right? Maybe it's possible to run these checks by somehow intelligently storing things on my stack, right? Does anyone have any ideas on how a PDA might do this? Like, what would a forward pass of a PDA through this input look like instead of a Turing machine? We want to check those three things again. Yeah? So one immediate design problem that you might run into is the fact that my Turing machine tests for multiple conditions, right? It makes sure that this, like, and what does it do? It rejects, or accepts rather, if it fails any of the conditions required to be an accepting computation, right? So, okay, this isn't the starting configuration, I reject. Maybe C3 doesn't follow from C2, I reject. And it can check all of these things up to the test of the final test to see if that contains Q accept, right? But I mean, like if I accept, right? If I'm a branch of computation of my PDA and I accept here, it's a little difficult, you know, or rather, what the key difficulty is what happens when I don't accept, right? Because after I check to see that C0 is the starting configuration, if it turns out it is, in fact, the starting configuration, then I'm not going to accept, right? I want to check to see if the other things are satisfied. But my PDA, you would imagine like, okay, it can't really do that now, right? Because once it accepts or rejects on any branch of computation, like that branch of computation is done. Yeah? But it's okay though, because PDAs are allowed to be non-deterministic. Aha, maybe we can leverage this. So maybe what our PDA can do is, okay, at the very beginning of my computation, I will non-deterministically check one of the three conditions to test. All right. So, okay, if I non-deterministically check for the, you know, making sure that C0 is the start configuration, then I can do that. And if it is the start configuration, that branch dies. In other words, it doesn't accept and it rejects, right? Because in order for a PDA to accept, because what we want is we want this PDA to reject when this is in fact a computation of M on W. But a PDA only rejects if all of its branches reject, right? In other words, if all of the conditions are met for being an accepting computation of M on W. So we have the non-determinism the right way around, right? And that's important. Okay, so I'm going to non-deterministically check for one of these three conditions to test, all right? But like, here's a problem. How do I non-deterministically test the second condition, right? Because there, what was my Turing machine doing? It was zigzagging back and forth. Yeah? And then it was doing the same thing for the next one. But the problem is my PDA can't backtrack, right? So once it reads here, I better have done something with my stack because I'm never going to be able to read this again, right? Okay, well, so the problem seems to be, can I test the equivalence more or less of these two strings minus what's happening around the tape head with a PDA? And if you remember way back when, we showed that for an arbitrary string, this was beyond the power of a PDA. right? It couldn't recognize the language W followed by an exact copy of W. But what it could, and like intuitively, the reason why is that like, okay, if I like pop everything here onto my stack, okay, I want to read the first character now here and make sure that it's the same as this guy. But what's the issue? This character that I stored is at the bottom of my stack now. So if I wanted to test it, I would need to empty everything, and then I wouldn't be able to test the rest of these guys. So what do we do instead? We know that testing if two strings are the same can't be done by a PDA, but testing if one string is the reverse of another string is something that can be done by a PDA, right? And so that's why when one modification that we're going to make to design a PW instead of an MW is we're going to encode our computation like this. Every other encoded configuration, we're going to store the reverse of that configuration. So that when my PDA non-deterministically decides, okay, I want to check to make sure that C2 follows from C3, it can pop C2 onto its stack, and it needs to test now that this character, the last character in C3, is the same as the last character in C2, but now that character is at the top of my stack. And so I can just pop down and make sure that this follows from this. And if at any point it doesn't, then I accept, right? So this is the key difference that is going to allow us to implement this with a PDA instead of a Turing machine, okay? So formally now, we're finally ready to give the proof of the undecidability of all PDA. And it looks very similar to the proof or the reduction that we gave from ATM to ALTM. The key difference now is that, oh, I guess this is a copy paste error. This should be sort of, right? We're going to have these reverse strings now in our encoding. Here's how our PDA is going to work. Non-deterministically choose to check one of the conditions necessary to be an accepting computation. So maybe it checks to see C0 as the starting configuration. Maybe it checks to see that each configuration follows from the previous one. And it can do that by non-deterministically picking a configuration to check, right? But then on the third case, the final thing that it can check is that QAccept is the state of CL. So it picks one of these things to do, one of these things to check, these conditions to check. And if the condition that I chose in step one does not hold, right, here, then I accept. Why? Because I want this PDA to accept every string if and only if M rejects on W, right? So the only possible string that this PDA couldn't accept, the only way all of these non-deterministic branches could reject and give me an input that I reject on is if, in fact, this input is an accepting computation of M on W. And now my reduction from all PDA is going to look like this. I just construct this description of PW now, my PDA, from M and W, and I feed it into my decider for all PDA, and I accept if it rejects, right? Otherwise, I accept. So this type of reduction that constructs some object, say a Turing machine or a PDA, as we saw, from the computation of a Turing machine, such that an object satisfies, one of those objects satisfies some property, such as accepting all strings, if and only if an accepting computation exists, this technique that we just showed, this is called a reduction via computation histories. It's not hard to see why it's called that, because we turned the possible computation histories into a language. Yeah. And next time, the reduction that we will give to prove that the post-correspondence problem is undecidable will be via computation histories. Oh, and why were we doing all this? Well, it was to show that EQTM was undecidable, right? First, we reduced that to showing all TM. We've just had to show all TM was undecidable, and we just showed how to do that. So if you just combine the statement that, well, all TM reduces to, or EQTM reduces to all TM, other way around, and all TM is undecidable, then I get that EQTM is undecidable. And to recap sort of where that leaves us, my screen would be so kind as to unfreeze. This is now what we have shown so far. Okay, it's kind of fleshed out version of the table that we saw at the beginning of the class. What we've shown now is we introduced this language all, right? And we showed that it was undecidable for Turing machines and PDAs. It turns out it is decidable for DFAs, and that's like a really simple proof that I didn't show here. And we accomplished this. Oh, and that allowed us to give a proof that EQ PDA was undecidable by first giving a reduction from ATM to all PDA, and then giving that reduction that we gave at the beginning of class from all PDA to EQ PDA. All right. And next time we're going to see, finally, we have reductions that are strong enough that we can leverage them to attack this post-correspondence problem that I talked about last time. Okay, and that's all. Oh, and we don't have class Monday. Just a reminder, it's Easter. So we'll meet again next Wednesday.